James Webb just photographed a planet being born. Right now, while you're reading these words, something is happening that almost nobody on Earth knows about. There is an object in the constellation Orion. It is not a planet. It is not a star. Not the way you think of a star. It is not a black hole, not a nebula, not a galaxy. It is a smear of collapsing gas. And inside that smear, in a ring roughly the width of our own asteroid belt, rock is being invented for the first time. Not moved, not melted. Invented. Gas is cooling into solid mineral, and those minerals are the first grains of a world that does not exist yet. That ring sits about 2 and a bit times the distance from the Earth to the Sun, 2.2 astronomical units. The temperature there is around 1200 Kelvin, which is hot enough to boil rock into vapor, and all of it is happening 1300 light years away, which means the light carrying this news left before England had a Norman king. Researchers are not describing this with words like interesting or promising. They are using the phrase T=0, the moment the clock starts, the beginning. This is the story of HOPS 315, and of what the James Webb Space Telescope actually saw when the headline said it photographed a planet being born. And here is the part the headlines are not telling you. It is not just what Webb found out there, it is what that finding says about the rock under your feet, which condensed out of vapor in exactly this way, 4.6 billion years ago. It is what is happening to that disk right now, in 2026, that almost nobody is discussing. And it is what is scheduled to happen at the end of this decade, on a mountaintop in Chile, that will decide whether any of this can be confirmed. Stay with me, because by the time this is over, you will never look at a rock the same way again. To understand why a smear of gas 1300 light years away matters, you have to go back to a night in northern Mexico. February 8, 1969. A fireball crossed the sky over the state of Chihuahua and broke apart above the village of Pueblito de Allende. It scattered stones across an area of desert scrub. Local people picked them up. Researchers arrived within days, and eventually more than 2 tons of material was recovered. It is called the Allende meteorite, and it is one of the most studied rocks in human history. The timing was almost absurd. NASA was months away from returning lunar samples, and laboratories across the world had just spent years building the instruments to analyze them. Those instruments were sitting ready. Then a free sample of the early solar system fell out of the sky and landed in the desert. What they found inside Allende changed planetary science. Embedded in the dark matrix of the meteorite were pale, irregular blobs, white inclusions, rich in calcium and aluminium. They had no obvious business being there. They were not fragments of a planet. They were not weathered debris. They were minerals that only form at extreme temperature, sitting inside a rock that had never been part of a world. They are called calcium-aluminium-rich inclusions, CAIs, and when they were dated, they came back as the oldest solid objects ever found in the solar system, roughly 4.567 billion years old. That number is the reason we say 4.6 billion years. Every time you hear the age of the Earth, you are hearing an echo of measurements made on grains like these. They are the 0 mark. Everything else in the solar system, including the planet you are standing on, is younger than those white blobs. Then came the question that took decades to answer. Where do they come from? The leading explanation was worked out in the early 1970s, largely by a young geochemist named Lawrence Grossman, then at the beginning of his career. His task was, on paper, extraordinarily boring. Take a cloud of gas with the composition of the sun, cool it, step by step, calculate which mineral crystallizes out first, then second, then third. Build a list. That is it. A cooling curve and a list of minerals. The list he produced predicted that the first solids to condense from a hot solar gas would be exactly the calcium and aluminium compounds found in Allende, in roughly the right order and roughly the right proportions. A thermodynamic calculation done at a desk matched a rock that fell out of the sky. That was the turning point. From then on, planetary science had a theory of how planet formation begins. Rock does not start as rock. It starts as vapor. It cools. It condenses. And the first grains that appear are the seeds of everything. But there was a limit built into that success, and it lasted more than 50 years. Every piece of evidence came from meteorites, from our own system, from a single sample of one. We had a theory of how planets begin, built entirely on rocks, from the only place where planets had already finished. Nobody had ever watched it happen somewhere else. Here is the chain, one step at a time. A cloud of cold gas and dust collapses under its own gravity. Most of the material falls inward and becomes a star. The rest cannot fall straight in, because it is rotating. It flattens into a disk. That disk is not calm. Material spirals slowly inward, and friction heats it as it goes. The closer to the star, the hotter it gets. Interstellar dust grains ride that inward flow. These grains are ancient, formed around dying stars long before this system existed. They drift in toward the heat. At around 1200 Kelvin, they stop being solid. 1200 Kelvin is roughly 2200 degrees Fahrenheit, which is hotter than flowing lava and hot enough to vaporize most common rock. The silicate grains sublime. They go from solid straight to gas. That gas contains silicon monoxide, silicon and oxygen, one atom each. It is the chemical signature of rock that has been boiled. Then the gas moves, or the disk cools, or the flow slows. And silicon monoxide gas does not simply stay gas. It recondenses. The atoms lock back together into crystal structures, and what comes out is not the amorphous dust that went in. It is crystalline mineral, forsterite, a magnesium silicate, chemically the same family as the green gemstone peridot. Those crystals are microscopic. Individually they are nothing, but they collide, and stick, and grow. Millimeters become centimeters. Centimeters become boulders. Boulders become kilometer-scale bodies. And once a body is large enough, its own gravity takes over, and it starts pulling in everything nearby. That is a planet. So the sequence is, dust falls in, dust boils into vapor, vapor cools into crystal, crystal grows into world. The vapor stage erases the history of the original grains completely. Whatever they were before, they are now raw material. There is one honest gap in that chain, and researchers will tell you about it before you ask. The step from centimeter-scale pebbles to kilometer-scale bodies remains difficult to explain. Pebbles that size tend to drift into the star before they can grow, and collisions between them tend to shatter rather than stick. This is usually called the meter-size barrier, and it has not been fully solved. We can see the beginning of planet formation, and we can see the end of it. The middle is still partly theory, but that first step, vapor condensing into crystal at around 1200 Kelvin, is the one that starts the clock. It is the step that produced the CAIs in the Allende meteorite. It is the step that dates our own system to 4.6 billion years. And until recently, it had never been observed anywhere except in rocks from our own past. Understand why this was close to impossible. The region where condensation happens is small. Around HOPS 315, the signal comes from inside 2.2 astronomical units. For scale, Mars orbits the Sun at about 1.5 astronomical units. So the entire zone of interest would fit comfortably inside the orbit of our own asteroid belt. Now put that region 1,300 light-years away. At that distance, 2.2 astronomical units, subtends an angle so small that no telescope currently in existence can produce a clean picture of it. You are not resolving a disk. You are not seeing a gap with a planet sitting in it. There is no photograph of a baby planet, and anyone who tells you otherwise is selling something. That is the first constraint. The second is worse. Young protostars like this are buried. HOPS 315 is a Class 1 protostar, which means it is still wrapped in the collapsing envelope of gas and dust that it is feeding on. That envelope is dense enough to hide the interior completely at visible wavelengths. Looking for chemistry inside it is like trying to read a label through a closed fist. Infrared light gets through where visible light does not, which is why Webb exists. But even infrared has a limit, and most protostars at this stage are simply opaque. HOPS 315 was observable for a reason that comes down to luck. The system is oriented in a way that leaves a gap in the envelope, and that gap happens to point toward us. Outflowing jets have cleared a cavity, and we are looking down it. Change the viewing angle by some tens of degrees, and there is nothing to see. It is a keyhole, and Earth happens to be standing at it. The third constraint is that a single telescope was not enough. Webb can measure chemistry with extraordinary precision. Its infrared spectrographs can identify specific molecules by the exact wavelengths they absorb and emit. What Webb cannot easily do at this distance is tell you where in the system a given molecule sits. Silicon monoxide near the star and silicon monoxide in a jet blowing away from the star look similar in a spectrum. That distinction is the entire argument. Silicon monoxide in a jet means nothing. It is common. Jets from young stars are full of it. Silicon monoxide sitting quietly in the inner disk, at 1200 Kelvin, alongside freshly crystallized silicates, means something else entirely. Resolving that required ALMA, the Atacama Large Millimeter Submillimeter Array, 66 radio dishes on a plateau in the Chilean Andes at 5,000 meters. ALMA can map where millimeter wavelength emission originates, with resolution far beyond what a single mirror achieves. So the observation needed three things at once: a telescope that could read the chemistry, an array that could locate it, and a system that happened to be tilted toward Earth at exactly the right angle, 1,300 light-years away. The result was published in Nature on the 16th of July, 2025, led by Melissa McClure of Leiden Observatory, with co-authors including Merrill Van Hoff and Logan Francis. The title is dry to the point of understatement. Refractory solid condensation detected in an embedded protoplanetary disk. What that means is this. Webb's infrared spectra of HOPS 315 showed a distinct band of silicon monoxide gas, and alongside it, the signature of crystalline silicates, including forsterite. Hot gas and fresh crystal, in the same place. ALMA then mapped the region and showed something critical. There is a silicon monoxide jet, a narrow beam shooting away from the star, and there is a separate reservoir of warm silicon monoxide low in the atmosphere of the disk, within 2.2 astronomical units, physically isolated from that jet. Two separate populations, one leaving, one staying. The one that is staying is the one that matters. That is rock in vapor form, sitting in the zone where planets assemble, at a temperature around 1200 Kelvin, in the process of turning back into solid. This is the first time any telescope has seen gas-phase silicon monoxide and freshly crystallizing silicates together in the same patch of a protoplanetary disk around another star. The comparison researchers reached for immediately was our own meteorites. The chemistry Webb detected, at the temperature Webb detected it, is the chemistry that produces calcium-aluminium-rich inclusions, the same white blobs found in Allende in 1969. The same grains that date our system to 4.6 billion years. We are not watching something exotic. We are watching the ordinary process that made the Earth, running again, 1,300 light-years away, from the beginning. What remains unexplained is the trigger. Researchers still cannot fully account for why this reservoir of hot vapor exists in the quantity observed, or how long such a phase lasts. If it is brief, catching it required extraordinary luck. If it is long, we should find more examples. Nobody currently knows which of those is true. Now, the correction. Because this is where the coverage went wrong. Webb did not photograph a planet at HOPS 315. There is no planet at HOPS 315, as far as anyone can demonstrate. There is not even a confirmed protoplanetary disk in the mature sense. There is an embedded disk inside a still collapsing envelope, and inside it, minerals condensing. The finding is the moment before planets. It is the raw material appearing. Calling it a photograph of a planet being born is like calling a photograph of a quarry a photograph of a cathedral. And here is the thing. The real result is more interesting than the exaggeration. Direct images of forming planets already exist. We have had them for years. What we did not have was the chemistry of the starting line. A picture of a young giant planet tells you that planet formation succeeded. It does not tell you how it began, or when, or from what. HOPS 315 tells you when the clock starts. That is why researchers use the phrase T equals 0. In our own system, T equals 0 is defined by CAI ages, 4.567 billion years, measured in a laboratory from a meteorite. At HOPS 315, T equals 0 is being observed live, in a system 1,300 light-years away, using light that left before the printing press, before gunpowder reached Europe, before most of the languages currently spoken on this planet existed in recognizable form. There is an honest caveat that goes with it. Detecting condensation does not guarantee planets. It shows the ingredients forming. Whether HOPS 315 ends up with rocky worlds, with gas giants, with a debris field, or with nothing at all, is unknown and will remain unknown for millions of years. We are not watching a planet form. We are watching a system become capable of forming one. To see the other end of the process, you go somewhere much closer. PDS 70 is a young star about 370 light-years from Earth. It is roughly 5 million years old. Our Sun is 4.6 billion years old, so PDS 70 has completed about 1/10 of 1% of the Sun's life so far. In human terms, it is a few days into infancy. Around it is a disk of gas and dust, with an enormous gap carved out of the middle. Inside that gap are two objects, PDS-70b and PDS-70c. Both are giant planets, both still forming, both still pulling in material. They are the most robust, directly imaged forming planets we have. Webb has been working on this system. On the 12th of February, 2025, a study led by Dory Blakely at the University of Victoria was published in the Astronomical Journal, using Webb's interferometric mode to detect both planets at a wavelength of 4.8 microns. That work sits within a guaranteed time program led by Doug Johnstone. Separately, Webb's NIRCam imaging as part of the MIND survey revealed a spiral structure in the disk connecting to the location of planet C. The straightforward interpretation is an accretion stream, a river of gas and dust flowing across the gap and feeding a disk that is formed around the planet itself. A planet with its own miniature disk, which is very likely how large moons are made. So the picture from PDS-70 is of planets that are eating, and the eating is not steady. Hubble observations in narrowband hydrogen alpha, comparing 2020 with 2024, found that the emission from PDS-70c more than doubled. That is an accretion signature. It means the rate at which the planet is swallowing material changed measurably within 4 years. 4 years. On a process that runs for millions. That is the vivid part. We tend to imagine planet formation as glacial, a slow accumulation over vast time. At PDS-70, it appears to be lumpy and violent, with bursts. The planet is not filling steadily like a bathtub. It is being fed in gulps. And there is one more detail. In the Webb interferometry data, there is a faint, unresolved source of light sitting inside the gap. Nobody knows what it is. It could be a spiral arm of gas and dust. It could be a third planet. Follow-up observations are required, and until they happen, the honest answer is that a point of light in that gap is unexplained. Put the two systems side by side, and the standard textbook sequence starts to look wrong in a specific way. The tidy model says, star forms first, envelope clears, disk settles, dust grows, planets assemble. Neat stages, in order. HOPS 315 breaks the first part of that. It is a Class 1 protostar, still buried, still accreting its envelope. The star is not finished. And yet the chemistry of planet formation is already underway, inside 2.2 astronomical units. The building has started before the site was cleared. PDS-70 breaks the last part. At 5 million years old, it already has 2 giant planets, and it may have a third. Giant planets are supposed to be difficult and slow to build, because you first need a solid core, and then you need to capture an enormous envelope of gas before the disk's gas disappears. 5 million years is fast for that. Both systems point in the same direction. Planet formation begins earlier and moves faster than the tidy version allows, and the same conclusion is being reached from our own meteorites. Ages measured on different classes of meteorite indicate that some parent bodies had already formed and melted within the first million years or so after the CAIs. Within a rounding error of 4.6 billion years ago, there were already objects large enough to have hot interiors. 3 independent lines of evidence. Chemistry in Orion at 1300 light-years. Imaging at 370 light-years. Isotopes in rocks in laboratories on Earth. All indicating the same thing, which is that the early phase is compressed. What remains genuinely unexplained is the mechanism that makes it fast. Getting from 1200 Kelvin vapor to a body large enough for gravity to matter in under 1 million years, without losing everything to inward drift, is still not fully accounted for. Pressure bumps, dust traps, and streaming instabilities are all proposed. None of them is settled. Now the part that is not about Orion. Every silicate mineral in the Earth's crust traces back through the same route: vapor, cooling, condensation, accumulation. The ground under your feet was, at one point, gas at roughly 1200 Kelvin. The iron in your blood, the calcium in your bones, and the silicon in the glass of the screen you are looking at, all passed through that stage. This is not poetry. It is the direct implication of the condensation sequence Grossman calculated in the early 1970s and the CAI ages measured from Allende. What HOPS 315 provides is the first outside check on that history. Every account we had of the first moments of our own system was reconstructed backwards from rocks. Reconstruction is powerful, but it is inference. and inference from one example is thin. Now there is a second data point, observed directly, 1,300 light-years away, in a system that had no contact with ours and no reason to behave the same way. It does behave the same way. Same molecule, same temperature range, same crystalline product, same location in the disk, inside 2.2 astronomical units, comparable to our asteroid belt, which is the region that later delivered water and metal to the inner planets. The chemistry of world-building appears to be generic. That is a large claim resting on a small number of observations, and it deserves the caveat. Two systems is still two systems. It is possible we have found the two most sun-like cases and are generalizing from them. Researchers are explicit that a survey of many embedded disks is needed before anyone can say the process is universal. That survey has not been done. But if it holds, the implication is straightforward. 4.6 billion years ago, in a disk very like the one now visible at 1,300 light-years, vapor at 1,200 Kelvin cooled and became the first grains of the Earth. And the same thing is happening tonight, in Orion, to material that will one day be the ground of a world nobody will ever name. Where does this go next? There is a hard limit on current instruments, and it is angular resolution. Webb and ALMA together got the chemistry and its location, but neither can produce an image of the inner 2.2 astronomical units of a disk at 1,300 light-years. That requires a larger aperture. That aperture is being built. The extremely large telescope is under construction in the Atacama Desert in Chile, with a primary mirror around 39 meters across. First light is planned for the end of this decade. When it operates, the resolution available for nearby star-forming regions increases substantially, and structures currently inferred from spectra may become structures that are directly seen. Between now and then, the work is repetition. Find more embedded disks. Look for the same silicon monoxide signature. Determine whether HOPS 315 is common or a freak. And on a longer time scale, the disk itself has a deadline. Protoplanetary disks do not last. Observations of star clusters of different ages indicate that most disks disperse within a few million years, cleared by radiation and winds. Whatever HOPS 315 is going to build, it is building against a clock. But even when that gas is gone, the process does not stop. The solids remain. They keep colliding. There is nothing to stop them. 1,300 light-years, 2.2 astronomical units, 1,200 Kelvin, 4.6 billion years, 4 numbers. A distance, a radius, a temperature, and an age. Between them, they describe the moment rock is invented, once in Orion where we can watch it, and once here, where we can only dig for the evidence. Webb did not photograph a planet being born. It photographed the chemistry of the instant before, in a place where no planet exists yet, around a star that is not finished forming. That is a smaller claim than the headlines made, and a much stranger one, because it means the beginning is not rare. It means the ground under your feet has a twin 1,300 light-years away, still in vapor, still cooling, still 4.6 billion years from becoming anywhere at all. If you want more space discoveries, explained without the exaggeration, subscribe and turn on notifications. Everything here is grounded in real published research rather than inflated headlines.